Across the vast universe, stars explode, galaxies collide, and black holes devour light. Yet among all these cosmic wonders exists something far rarer. An event so powerful it outshines entire galaxies, so brief it vanishes in days, and so mysterious that scientists once doubted it was real. It forges gold, platinum, and the heaviest elements in existence, treasures born from cosmic violence. And in all of human history, we've only seen it happen twice. This is the Kilonova, the rarest, most powerful explosion in the universe. And if you want to know everything about it, then watch this video till the end and subscribe to the channel. Let's begin. A kilonova is not just another explosion in space. It is the universe's most extraordinary display of destruction and creation combined. When two neutron stars, the dense corpses of long-dead massive stars, spiral into one another after an eternity of orbiting, their final embrace unleashes a storm of energy unlike anything else in the cosmos. Sometimes, instead of two neutron stars, it's a neutron star colliding with a black hole. But the result is always the same: a cosmic detonation that bends space-time itself and floods the universe with both light and gravitational waves. In that single instant, matter is ripped apart and reshaped under unimaginable forces. The explosion releases more energy in seconds than our Sun will emit over its entire 10 billion year lifetime. From the outside, it appears as a brief but intensely bright burst, a flash that can momentarily outshine entire galaxies before fading into the dark. Yet within that blinding flare lies the story of creation itself, because this is where new elements are born. A kilonova's power doesn't just lie in its light, but in its consequence. It forges the building blocks of worlds: gold, platinum, and the heaviest materials we know, elements that can't be made in ordinary stars. It's as if the universe, through violence and chaos, chooses to create beauty and value. This is what makes the kilonova so profound. It is both an ending and a beginning, a cosmic alchemy of death turning into creation. At first glance, a kilonova might sound similar to a supernova. After all, both are stellar explosions of unimaginable scale. But while a supernova marks the death of a massive star, a kilonova represents something far more exotic: the violent union of two remnants that a supernova leaves behind. In a sense, a kilonova is what happens after a supernova, when two neutron stars, the leftover hearts of exploded stars, finally collide after millions or even billions of years of circling one another. Supernovae, though awe-inspiring, are almost routine by cosmic standards. Astronomers observe several supernovae each century within our galaxy, and countless more in distant galaxies every year. Their light can linger for months, their patterns well understood, their behavior somewhat predictable. But a kilonova? That's a whole different story. These events are so rare and fleeting that humanity has confirmed only about 2 of them in recorded history. They blaze across the sky with a brilliance that surpasses a supernova, but only for a matter of days, a brief, breathtaking whisper before fading back into cosmic silence. In terms of energy, both are immensely powerful, yet the nature of that energy differs. A supernova tears a star apart through nuclear fusion, while a kilonova bends space-time and releases bursts of gravitational waves rippling through the fabric of the universe. One is the spectacular death of a single star. The other, the final fatal dance between 2 stellar corpses. If supernovae are the fireworks of the cosmos, kilonovae are the rare jewels hidden within, the kind of event that astronomers can spend lifetimes waiting to see just once. To understand the true power behind a kilonova, we must first understand the extraordinary nature of the objects that create it: neutron stars. When a massive star, many times larger than our Sun, reaches the end of its life, It can no longer sustain the nuclear reactions that keep it from collapsing under its own gravity. As the star's core implodes, its outer layers are violently expelled into space in a supernova explosion. What remains is a core so dense, so extreme, that it defies imagination. That remnant is a neutron star, one of the most bizarre and fascinating entities in the universe. A neutron star is the collapsed heart of a once-living sun. It may only be about 20 kilometers across, roughly the size of a city, but within that tiny sphere is a mass greater than that of our entire sun. The density is beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons, as much as a mountain compressed into a droplet. It is matter stripped to its fundamental components, atoms crushed so tightly that protons and electrons fuse into neutrons, forming an enormous, solid ball of nuclear matter. In essence, a neutron star is a single gigantic atomic nucleus held together not by chemical bonds, but by the unyielding force of gravity. The conditions inside such a star are nothing short of cosmic madness. The surface gravity of a neutron star is about 200 billion times stronger than that of Earth. If you were to stand upon its surface, which of course no human or spacecraft could survive, your body would be flattened into atomic dust in less than a microsecond. The magnetic fields surrounding these stars are so intense they can rip electrons out of atoms and twist space itself into spirals of radiation. Many neutron stars spin at mind-bending speeds, hundreds of times per second, emitting beams of radiation like cosmic lighthouses. These are known as pulsars, and their rhythmic flashing once mystified astronomers into briefly considering they might be signals from alien civilizations. What makes neutron stars so astonishing is how they bridge the gap between ordinary matter and the physics of black holes. They represent a frontier of physical law, a state of matter that cannot be recreated on Earth. Deep within their cores, scientists believe that neutrons might even dissolve into their subatomic components, forming a sea of quarks, or something even more exotic that we can only theorize about. They are laboratories of extreme physics, where gravity, quantum mechanics, and nuclear forces all collide in ways that challenge our understanding of nature. But neutron stars rarely exist in isolation. Sometimes, when two massive stars are born together, they live their lives as a binary pair, orbiting each other in a cosmic waltz. Each star eventually dies in a supernova, and both leave behind neutron stars. Bound by gravity, these remnants continue their ancient orbit, circling closer and closer over eons as they emit gravitational waves, ripples in space-time that drain their orbital energy. Slowly but relentlessly, their paths decay, and the two ultra-dense stars begin an inescapable fall toward one another. It's a process that can take hundreds of millions or even billions of years. Yet once it begins, nothing can stop it. Every second of that long cosmic countdown brings them closer together, increasing their speed, tightening their orbit, and intensifying their gravitational grip. The final moments are a furious spiral of unimaginable violence, where each neutron star whips around the other at a fraction of the speed of light. In these last seconds, the universe holds its breath, because what follows is the rarest explosion of all. When their collision finally happens, it is the beginning of something far greater, the birth of a kilonova. And so, to understand why kilonovae are so extraordinary, we must appreciate what neutron stars truly are, not just remnants of dead suns, but the most extreme physical objects we can observe. They are nature's densest stones, spinning relics that embody the aftermath of cosmic death and the potential for cosmic rebirth. When two of these titanic remnants collide, the energy they release shakes the very fabric of space-time, lighting up the universe with a brilliance few will ever witness. In those fleeting moments, the elements that make up planets, mountains, and even the gold on our hands are forged from the collision of two dead stars. It's as if the universe itself remembers that even in its darkest corners, creation and destruction walk hand in hand. Once we understand the incredible nature of neutron stars, it becomes easier to imagine the cosmic choreography that leads to a kilonova. After two massive stars are born together in the same stellar nursery, their lives are intertwined from the very beginning. They grow, burn their fuel, and eventually die in brilliant supernova explosions. But their bond doesn't end with death. What's left behind are two neutron stars, still gravitationally bound, locked in a mutual orbit that will last for millions or even billions of years. What begins as a calm cosmic dance gradually transforms into a slow, spiraling march toward annihilation. These twin remnants are among the densest objects in existence, each no larger than a city, but with masses greater than that of our Sun. Their gravitational pull on each other is immense, and with every orbit they distort space-time, sending out ripples, gravitational waves that travel across the universe at the speed of light. These ripples carry away a tiny amount of energy from the system, causing the neutron stars to inch closer together over time. The process is imperceptibly slow, but it is relentless. Each orbit drains them of orbital energy, and as they draw nearer, they begin to orbit faster and faster. It is a gravitational ballet that spans eons, and yet it is utterly silent, invisible to all but the most sensitive instruments in the cosmos. For billions of years, nothing about their motion would seem out of the ordinary. They would appear frozen in an eternal loop, circling each other endlessly, emitting their soft but constant stream of gravitational whispers into the void. But those whispers add up. Eventually, after countless revolutions, the separation between them shrinks from thousands of kilometers to mere hundreds, and then to just a few dozen. Now, each star's gravity begins to deform the other, pulling at its dense surface, twisting its magnetic fields, and igniting torrents of radiation. The system becomes a cauldron of gravitational tension, each second more violent than the last. By this point, the two neutron stars are orbiting each other dozens of times per second. The energy in their motion is unimaginable, a storm of mass and gravity spinning on the edge of physics itself. Their approach becomes a spiral of doom, one that can no longer be stopped by any force in nature. This is the prelude to a kilonova, a setup billions of years in the making. The space around them becomes a battlefield of intense forces. Gravitational waves grow stronger, space-time trembles, and even light bends under their mutual pull. To an outside observer, if such a thing could ever be seen directly, it would be the most mesmerizing sight in existence. Two tiny, invisible stars drawing closer, faster and faster, glowing faintly as tidal forces rip particles and radiation from their surfaces. In those final hours, the pair emits gravitational waves so powerful that they could be detected across the entire observable universe. Astronomers using observatories like LIGO and Virgo can capture these ripples and read them like a cosmic message, a signal that somewhere two neutron stars are approaching the end of their ancient orbit. These signals allow scientists to estimate their masses, their distances, and even predict the moment when their collision will occur. It's as though the universe itself is sending out a warning. Something extraordinary is about to happen. And yet, there's a haunting beauty in this slow approach. For billions of years, these two dead stars have circled in silence, drawing ever closer until their fates are sealed. Every orbit brings them nearer to their end and their beginning. Because in the instant they finally meet, the universe will be forever changed. It's a setup of perfect symmetry, two remnants of death destined to collide and give birth to new elements, new energy, and perhaps even new worlds. This is the moment before the storm, the quiet inhale before the cosmic breath releases its most powerful exhalation. From this eternal dance comes one of the rarest spectacles in existence, a collision that will light up galaxies and echo through space-time. It's as if the cosmos itself saves its greatest performance for last. Two stellar ghosts, locked together since birth, coming home to one final, breathtaking embrace. The long, slow spiral of two neutron stars eventually gives way to a moment of violent, breathtaking climax, the final dance. After billions of years of circling one another in the dark, the last few seconds of their existence are a frenzied blur of motion, energy, and warped space-time. In those final instants, the two stars move so fast that they complete dozens of orbits every second, their speed approaching a significant fraction of the speed of light. The gravitational waves they release now thunder through the universe with unimaginable force, shaking the very fabric of reality. As they draw closer, tidal forces rip across their surfaces, stretching and compressing them like taffy made of pure nuclear matter. Their crusts crack, magnetic fields twist into knots, and matter is stripped away in glowing streams that spiral outward into space. Each star's immense gravity distorts the other into teardrop shapes, and the immense pressure at their cores begins to reach a breaking point. The airless void around them vibrates with energy. Space-time itself ripples like water in a storm. In this moment, the universe witnesses something that almost defies description. Two fragments of collapsed suns dancing faster and faster, circling each other at nearly the speed of light, until the distinction between matter and energy begins to blur. The final few milliseconds before impact are among the most violent phenomena nature allows. The neutron star's magnetic fields, billions of times stronger than any magnet on Earth, collide and twist together, unleashing flashes of gamma rays and high-energy particles. The curvature of space-time around them becomes so extreme that even light struggles to escape the warping effects of their gravity. To a distant observer, it would appear as if the stars were dissolving into one another, their edges smeared and distorted by relativistic effects. Time itself, near their surfaces, begins to stretch and slow, the ultimate consequence of Einstein's theory of relativity playing out in real time on a cosmic stage. For those last fleeting moments, the power being generated is almost incomprehensible. Each orbit radiates more energy in gravitational waves than all the stars in our galaxy produce in light combined. If you could somehow listen to those waves, which is precisely what instruments like LIGO and Virgo do, you would hear a rising chirp in frequency and amplitude, a gravitational crescendo building toward its final fatal note. That sound, recorded in 2017 during the first confirmed Kilonova, lasted just a fraction of a second. And yet it told the story of two stars that had been orbiting one another for billions of years. And then, suddenly, it happens. The distance between the stars shrinks to zero. The immense masses that once orbited each other at breakneck speed now collide in a cataclysmic flash. In less than a heartbeat, their combined mass collapses inward, fusing and releasing a burst of energy that outshines entire galaxies. The force of the collision blasts matter into space at a significant fraction of the speed of light, forming a shockwave of radiation and subatomic particles. The surrounding space ignites with the glow of freshly synthesized elements, and a beam of gamma rays shoots across the universe, the first visible sign of what we call a kilonova. But even in this chaos, there is elegance. The collision is both the end and the beginning, the final note in a cosmic symphony that has been playing since the dawn of time. The two neutron stars, after billions of years locked in orbit, merge into one, either forming a black hole or a new, even more massive neutron star that teeters on the edge of collapse. The energy of their motion, the violence of their destruction, and the brilliance of their light all serve one purpose: to give birth to something new. In the cosmic silence that follows, space-time slowly smooths back into shape. Gravitational waves dissipate into the void, and light from the explosion begins its long journey across the universe, perhaps to reach our telescopes millions of years later. It's the final dance of two dead suns, their last embrace immortalized in waves and light. A story of destruction that becomes creation, written not in words, but in gravity itself. When the two neutron stars finally collide, the universe witnesses one of the most violent, transformative, and short-lived events in all of cosmic history. After their endless spiral of gravitational attraction, a dance that took billions of years to reach its finale, the stars meet in a fraction of a second. The collision itself is not a simple impact like two rocks colliding in space. It's more like two mountains of pure nuclear matter smashing together at nearly the speed of light, releasing an explosion so intense that even the laws of physics seem to tremble under its weight. This is the birth of a kilonova, a flash so powerful that for a brief instant it can outshine an entire galaxy. At the exact moment of impact, unimaginable forces tear through the merging stars. The gravitational fields surrounding them, already extreme, now interact in chaotic ways that stretch and twist space-time itself. Their immense masses compress further under their mutual gravity, momentarily forming a single, hypermassive object, a swirling maelstrom of neutron-rich material hotter than any furnace in the cosmos. Temperatures surge to over 1 billion degrees, and matter is ejected at a significant fraction of the speed of light. This explosion unleashes a torrent of radiation, including bursts of gamma rays, the most energetic form of light known. These gamma ray bursts, often lasting less than 2 seconds, can travel across billions of light years, reaching Earth long after the explosion has faded from view. This brief gamma ray flash is often the first signal we detect of a kilonova's birth. It marks the exact instant when two neutron stars' dense cores violently merge and begin spewing their innermost materials into the surrounding space. These bursts are so bright that they briefly outshine everything else in their host galaxy. For astronomers, such signals are like cosmic fingerprints, rare, fleeting signatures that reveal one of the most secretive processes in the universe. Yet, the gamma rays are only part of the story. What follows in the seconds and minutes after the impact is a phenomenon of staggering complexity. The collision throws out jets of material, streams of neutron-rich matter that erupt from the poles of the newly formed remnant. These jets, powered by magnetic fields trillions of times stronger than Earth's, accelerate particles to near-light speeds, shaping the gamma-ray burst into narrow beams that pierce through space. Meanwhile, around the equator of the merging object, matter is flung outward in vast tidal plumes, forming clouds of subatomic particles so dense that they immediately begin to forge new elements. This is one of the universe's most sacred forges. Inside this inferno, atomic nuclei are bombarded by neutrons in a process known as rapid neutron capture, or the R process. In this brief window of time, elements heavier than iron, gold, platinum, uranium, and others, are born in enormous quantities. Each atom of gold that will one day end up in a wedding ring, each speck of platinum found deep in Earth's crust, each grain of rare heavy metal in distant planets, all of them can trace their origin back to moments like this. Within just a few seconds, the Kilonova manufactures more precious metals than all the stars in an entire galaxy could create over millions of years. The collision itself doesn't just produce light, it also shakes the very fabric of space-time. The merging neutron stars emit gravitational waves that ripple outward, carrying information about their mass, spin, and the violence of their merger. These waves travel across the cosmos untouched, eventually reaching detectors like LIGO and Virgo here on Earth. When scientists record these ripples, they can effectively listen to the universe, hearing the deep, resonant thrum of two stars merging. The data from these waves tells us exactly when and how the collision occurred, while telescopes around the world race to catch the accompanying light before it fades. As the ejected material expands into space, it begins to cool and glow, producing the luminous flare we see as a kilonova. For a few hours to a few days, the explosion radiates with a brightness 1,000 times greater than that of a nova. But this brilliance fades quickly. The debris cloud, rich in heavy elements, transitions through a series of colors as it cools. First, an intense blue from the hottest regions, then fading to red, and finally to infrared as the elements recombine and scatter the light. Within a week, the spectacle vanishes, leaving behind only the afterglow, a faint memory of the cataclysm that once illuminated an entire galaxy. Inside the wreckage, something extraordinary forms. Depending on the exact masses of the two neutron stars, the result may be either a black hole, a region so dense that not even light can escape, or a hypermassive neutron star temporarily supported by its rapid rotation and magnetic fields. If a black hole forms, it immediately begins to swallow the surrounding debris, releasing more energy and stabilizing the system. If a neutron star survives, it spins at incredible speed, its surface glowing with heat and magnetic activity before possibly collapsing into a black hole minutes or hours later. In both outcomes, the universe is forever changed. Energy, matter, and elements have been redistributed in a single cosmic act of creation through destruction. It's hard to grasp the scale of what just happened. In less than a second, this collision releases as much energy as all the stars in the observable universe combined emit in that same instant. For comparison, if we could harness even a fraction of that power, it would dwarf anything humanity could ever produce. All the nuclear weapons ever built would seem like sparks next to this cosmic detonation. Yet, despite its unimaginable violence, the kilonova is an act of creation. Out of the chaos comes order. From destruction arises beauty. It's a reminder that the universe's most violent moments are also the ones that give birth to its most precious materials, the elements that make planets, oceans, and life itself possible. When astronomers detected the kilonova of 2017, they realized they were witnessing not just the death of two stars, but the cosmic origin story of matter itself. Every photon, every gravitational wave, every atom of gold that would later cool in the debris was a direct result of that collision. In a sense, we are all connected to these events. The calcium in our bones, the iron in our blood, the gold in our jewelry, all forged long ago in the hearts of merging neutron stars. And as the light from a kilonova travels for millions or billions of years through space, it eventually reaches us, a faint whisper from the universe's rarest forge, reminding us that even in death, the cosmos creates, that the rarest events can leave the most lasting marks, that two dead stars, colliding in the void, can shape the very fabric of life and beauty across the universe. When the fury of a kilonova fades and its light begins to dim across the cosmos, what remains is not emptiness, but creation. In the heart of that explosion, the universe performs one of its rarest and most sacred acts, the birth of heavy elements. These few seconds of cosmic violence, born from the collision of two dead stars, give rise to the treasures that define worlds: gold, platinum, uranium, and all the other heavy metals that fill the periodic table beyond iron. Without kilonovae, the universe would be a much duller, simpler place, one without precious metals, without rocky planets, and quite possibly without life as we know it. To understand how this happens, we must look deep inside the Kilonova's core, that hellish crucible where matter is ripped apart and rearranged. When the two neutron stars collide, they eject enormous amounts of material enriched with neutrons, those uncharged particles that make up most of an atom's mass. This neutron-rich debris expands outward, and in that expansion, one of the most extraordinary physical processes unfolds, the rapid neutron capture process, or R process. It's a cosmic assembly line where atomic nuclei are bombarded by neutrons faster than they can decay. In fractions of a second, these nuclei grow heavier and heavier, forming the rarest elements in existence. In that single violent moment, nature forges billions of times more gold and platinum than could ever be made inside ordinary stars. These elements cannot form in normal stellar furnaces. Even the most massive stars cannot sustain the kind of neutron density required. Only the merger of two neutron stars can provide the perfect conditions: immense pressure, extreme temperature, and an ocean of free neutrons. The collision acts as a kind of cosmic forge, manufacturing elements that become the raw materials for future planets, moons, and civilizations. Imagine the gold in a wedding ring. It glimmers softly, a symbol of permanence and love, yet its origin is anything but gentle. That gold was born in chaos, in the heart of a cosmic explosion that shattered the calm of space-time. Billions of years ago, two neutron stars collided in some distant galaxy, and in that instant, atoms of gold were hurled into the void. Over eons, those atoms drifted through space, mingling with clouds of gas and dust, until gravity gathered them together into a new solar system, ours. Those same atoms eventually found their way into the crust of our planet, where humans, eons later, mined them, shaped them, and gave them meaning. So when you hold gold, you are literally holding the ashes of dead stars. But gold is only part of the story. Platinum, uranium, and countless other rare elements share the same stellar origin. The platinum used in electronics, the uranium that powers reactors, even the iodine that runs through human veins, all were born in the same cosmic fires. The periodic table, with all its richness and diversity, is a record of the universe's creativity, its willingness to turn chaos into complexity. Every element heavier than iron tells a story written in the language of starlight and time, a story that begins with destruction and ends in creation. For billions of years, these elements have traveled across galaxies, seeding young stars and planetary systems. Without them, rocky planets like Earth could not exist. The iron in our blood, the copper in our wiring, the silver in our mirrors, all owe their existence to ancient Kilonovae. Every atom around us is part of a cosmic genealogy, an inheritance of stars. The universe is not simply vast and empty. It's a family tree of explosions, mergers, and rebirths, each generation of stars giving rise to the next. What makes this even more poetic is the rarity of the process. Kilonovae happen perhaps once every 100,000 years in a single galaxy. Yet their contributions shape entire worlds. Each event scatters its newly formed elements across light years of space, enriching its host galaxy in a slow, steady rhythm of creation. Over cosmic time, the accumulation of these rare collisions fills the universe with the materials necessary for planets, for oceans, for people. So in a very real sense, we are all descendants of Kilonovae, beings made from the heavy elements forged in those long-ago cosmic collisions. Even the heaviest and most unstable elements, like uranium and thorium, which heat Earth's interior and drive the movement of its continents, are gifts of these stellar mergers. Without them, our planet might have cooled long ago, becoming geologically dead and lifeless. The gold in our jewelry, the uranium in our rocks, the iron in our blood, they are all echoes of a single truth. Life itself is a product of cosmic destruction. The next time you see a piece of gold glinting in the light, think of what it truly is. Not just a metal, but a remnant of two stars colliding in a distant galaxy billions of years ago. Its beauty isn't just in its color or its shine, it's in its story. A story written across space-time. A story of chaos transformed into permanence. A story of the universe's ability to turn death into creation. Every ring, every coin, every spark of heavy metal on Earth is a silent relic of a kilonova. A tiny, tangible connection to an event so rare and so powerful that it redefines what creation means. In those fleeting cosmic moments, when two neutron stars collide and the universe burns brighter than a billion suns, the very building blocks of existence are made. That is the legacy of a kilonova. Not just light and energy, but matter itself. The gold we prize, the atoms we rely on, the world we inhabit, all of it is the aftermath of the rarest explosions in the cosmos. When the collision of two neutron stars finally settles, when the shockwaves of energy and the tidal plumes of ejected matter begin to spread into the surrounding void, something truly mesmerizing occurs. The universe lights up with one of the most spectacular but fleeting phenomena ever witnessed: the glow of a kilonova. For a few short days, the aftermath of this violent event becomes one of the brightest objects in the cosmos, shining with the combined brilliance of billions of suns. It's a light so intense that for a brief moment, it can outshine an entire galaxy. And yet, it's gone almost as quickly as it appears. A cosmic flashbulb that illuminates the night sky of the universe before fading back into darkness. The light of a kilonova is not a steady beacon. It's a transient flare born from the radioactive decay of newly forged elements. When the neutron-rich material blasted from the collision begins to expand into space, it undergoes rapid nuclear transformations. The unstable atomic nuclei formed in the explosion release energy as they decay, producing an enormous outpouring of heat and light. This radioactive afterglow, the kilonova's optical signature, is the universe's announcement that new matter has been born. In those early hours, the heat of decay makes the surrounding debris blaze at temperatures of tens of thousands of degrees. The result is a dazzling blue-white light that radiates outward into the void, reaching across millions or even billions of light years. But the spectacle is heartbreakingly brief. Within a matter of days, the ejected material cools and the light begins to change. The initial blue glow, produced by lighter elements, quickly gives way to redder hues as heavier elements like gold, platinum, and lanthanides dominate the spectrum. These elements absorb and scatter light, causing the brightness to fade even faster. Astronomers describe this as a color evolution, a transition from blinding blue to fiery red to faint infrared, all unfolding over the course of a single week. It's like watching a cosmic sunset in fast forward, a brilliant flame flickering out into the darkness. Capturing this fleeting light is one of the greatest challenges in modern astronomy. Kilonovae occur without warning, often in galaxies hundreds of millions of light years away, and their brilliance lasts for only a handful of days before vanishing. By the time telescopes swing into position, the light may already be fading. That's why astronomers rely heavily on gravitational wave detectors like LIGO and Virgo to give them an early signal, the faint ripples in space-time that precede the burst of light. These ripples act like an alarm bell for the universe, telling scientists where to look and when. Only through this coordination, gravitational waves first, light second, can humanity hope to capture the elusive glow of a kilonova before it disappears forever. When a kilonova does appear in our instruments, the beauty of its light is unlike anything else in the sky. It's not the steady brilliance of a star, nor the drawn-out fade of a supernova. It's a burst, a radiant, breathtaking bloom of light that announces the creation of new elements and then retreats into silence. It shines roughly 1,000 times brighter than an ordinary nova, but while a nova can linger for weeks or months, a kilonova burns with furious intensity and then fades within days. The universe doesn't linger on these moments. It simply flashes, as if showing us its power for just long enough to remind us that even the briefest things can be the most magnificent. For astronomers who have witnessed a kilonova's light firsthand, it's an experience that borders on the spiritual. The brightness itself tells a story of unimaginable violence, of creation through chaos, of ancient neutron stars giving up their existence to forge something new. And to think that this light has traveled across millions of years, crossing the vast emptiness of intergalactic space just to reach our telescopes, is humbling beyond words. By the time it reaches Earth, that light is already ancient. The explosion it came from may have occurred before humans even existed, before Earth had continents shaped as they are today. Yet when that faint glow is finally captured by our instruments, it connects us across time, a signal from the deep past shining for a moment in our present. It's almost poetic that something so brief can leave such a lasting mark. The light of a kilonova, though fleeting, carries within it the fingerprints of the universe's evolution, a record of the elements being formed, of space-time being stretched, of physics being rewritten in real time. Every photon that escapes from the explosion tells a part of that story, revealing not just what happened, but what the universe itself is capable of. This is why kilonovae are so rare and so important. They are not just cosmic events. They are messages, illuminating the darkest corners of the cosmos for just long enough to be seen before fading into eternity. And when that light finally fades, when the blue turns to red and the red dissolves into the black, the universe grows quiet again. What remains is the aftermath, the newly formed elements drifting through space, the gravitational ripples spreading outward, and the silence of cosmic peace returning to the scene of unimaginable violence. The light may vanish, but its legacy endures. Somewhere, deep in the future, the matter it created will become part of a star, a planet, or maybe even a living being. The kilonova's glow reminds us that beauty and impermanence are inseparable in the cosmos. The universe creates brilliance, only to let it fade, and in doing so, it writes the story of existence itself. Every flash, every burst, every photon carries the echo of creation, proof that even the rarest, shortest-lived events can light up eternity. Catching the light of a kilonova is like witnessing a ghost, rare, brief, and nearly impossible without knowing exactly where to look. For most of human history, such events were invisible, hidden within the black fabric of the universe, their light too fleeting and their signals too faint to notice. But in the last decade, something extraordinary changed. Humanity developed the tools not just to see the universe, but to listen to it. The discovery of gravitational waves, ripples in the very fabric of space-time, opened an entirely new sense for astronomy. And when we began to combine those waves with light, radio, and gamma-ray observations, a new era was born: multi-messenger astronomy, the science of detecting the undetectable. Gravitational waves are unlike anything we can observe with telescopes. They don't come in the form of light, or particles, or radiation. They are literal distortions of space-time, stretching and compressing the universe itself as they pass through. When massive objects like neutron stars or black holes orbit each other, they emit these waves, slowly losing energy until they finally collide. For billions of years, those ripples travel outward, weakening as they go, yet still detectable when they reach Earth, if we have instruments sensitive enough to hear their faint hum. That's where detectors like LIGO, Laser Interferometer Gravitational Wave Observatory in the United States and Virgo in Italy come in. These observatories don't look at the sky, they measure movement. Using laser beams shot through miles-long tunnels, they can detect distortions in space-time smaller than a fraction of a proton's width. When a gravitational wave passes through Earth, it slightly alters the length of these tunnels, and that tiny change is recorded as a signal, a whisper from the universe. These signals are incredibly faint, but unmistakable in their pattern, a rising chirp that grows in frequency and intensity as two objects spiral toward collision. When LIGO and Virgo detected one such chirp on August 17, 2017, the world of astronomy changed forever. The signal, named GW170817, lasted just over 100 seconds. But that brief vibration carried with it a story of two neutron stars in their final death spiral. Almost instantly, alerts went out across the world. Dozens of telescopes, both on the ground and in orbit, swiveled toward the region of sky where the signal had originated. Then, just 1.7 seconds after the gravitational wave detection, something incredible happened. A short burst of gamma rays was recorded by NASA's Fermi satellite. That flash of light was the visual counterpart to the gravitational waves. The same event, seen through a completely different cosmic messenger. This was the first time in history that an event in the universe had been observed in both gravitational waves and electromagnetic light. The implications were staggering. It confirmed that the source of short gamma-ray bursts was indeed the merger of neutron stars, something that had long been suspected but never proven. It also demonstrated that gravitational wave astronomy could pinpoint phenomena that traditional telescopes would never find on their own. Together, they painted a complete picture of a single event, uniting sight and sound into one coherent cosmic story. From that moment forward, astronomy was no longer a one-sense science. It became multisensory, a field capable of perceiving the universe in entirely new ways. Gravitational waves tell us about the invisible motions and masses of objects, while electromagnetic signals, visible light, X-rays, radio waves, gamma rays, reveal their structure, temperature, and composition. By combining these messengers, scientists can reconstruct an event from every angle. It's like watching a silent movie suddenly gain sound, revealing layers of meaning that were always there but never heard. In the case of a kilonova, this synergy is especially important. The gravitational waves serve as an early warning system, alerting astronomers that two massive objects are spiraling toward collision. Once detected, telescopes worldwide begin scanning that patch of sky, waiting for the faint optical flash that signals the explosion itself. Within hours, observatories across the electromagnetic spectrum, from radio dishes to space-based X-ray telescopes, converge their gaze on the same coordinates. The data they collect offers a complete timeline of the event. The gravitational waves reveal the star's approach. The gamma rays capture the collision. The visible light shows the radioactive glow of new elements, and the radio signals trace the expanding debris long after the explosion fades. This combined approach has revolutionized our understanding of the cosmos. We no longer have to rely on light alone to know what's happening in the distant reaches of space. Gravitational waves can pass through dust, gas, and darkness unimpeded, bringing us information from places that light could never escape. It's as if the universe, for the first time, is speaking to us directly, and we finally have the instruments to listen. But the true magic lies in how coordinated this process has become. When LIGO or Virgo detect a gravitational wave, an automated alert goes out within seconds to observatories all over the globe. In a matter of minutes, the entire astronomical community is mobilized. Telescopes in Chile, Hawaii, South Africa, and space itself begin searching the sky. In 2017, this global collaboration led to over 70 observatories observing the same event, each one contributing a different piece to the puzzle. Together, they built a comprehensive image of the Kilonova, not just as a light source, but as a full, dynamic story written across space-time. This ability to detect the undetectable, to find an explosion that lasts mere days and happens billions of light years away, is one of humanity's greatest scientific achievements. It required the combined effort of thousands of researchers, the most precise instruments ever built, and the unifying goal of understanding our universe on its most fundamental level. Through gravitational waves and electromagnetic light, we have learned to hear and see the cosmos at once, to catch the briefest, rarest signals from events that shape everything we are. And perhaps the most profound part of this story is that every time we detect a kilonova, we are watching history in real time. We are witnessing the birth of matter, the bending of space-time, the confirmation of theories written by Einstein a century ago, and the forging of the elements that make up our world. We are, quite literally, observing the universe creating itself. The story of how humanity first witnessed a kilonova, not as theory, not as speculation, but as an undeniable cosmic event, begins on an otherwise ordinary day in August of 2017. For decades, astrophysicists had predicted that somewhere in the depths of space, two neutron stars would one day collide, creating both a burst of light and a ripple in space-time. Yet no one had ever seen it happen. Supernovae had been captured, black holes detected, even exoplanets mapped. But the fabled neutron-star merger remained an elusive dream. That all changed on August 17, 2017, when the universe finally decided to reveal one of its rarest secrets. At precisely 8:41 a.m. Eastern Daylight Time, the twin detectors of LIGO, one in Washington State and one in Louisiana, along with the Virgo Observatory in Italy, registered a faint but distinct gravitational wave signal. It wasn't the signature of colliding black holes, which LIGO had already become famous for detecting in 2015. No, this signal was different. It lasted much longer, around 100 seconds, and its frequency pattern rose like a chirp, a telltale sign of two lighter objects spiraling toward each other. The data analysis came back quickly. This was the death dance of two neutron stars, each about 1.4 times the mass of our Sun, locked in a final fatal orbit, some 130 million light-years away in a galaxy called NGC 4993 in the constellation Hydra. For the first time in history, humans were not just hearing the gravitational heartbeat of a dying stellar pair, they were about to see it too. Just 1.7 seconds after the gravitational waves washed over Earth, NASA's Fermi Gamma Ray Space Telescope detected a short, sharp burst of gamma rays coming from the same patch of sky. This coincidence was staggering. Two completely different instruments, one listening to gravity and one watching light, had recorded two signals separated by less than 2 seconds. A cosmic handshake between Einstein's theory and the observable universe. It was as if space-time itself had spoken and then, immediately after, shown its face. The alert went out to every observatory on Earth. Within minutes, telescopes around the world and in orbit began scanning the region of sky where the event was thought to have occurred. But this was no easy task. The source was somewhere within an area covering hundreds of square degrees of the sky, and the clock was ticking. The light from a kilonova fades quickly. Astronomers knew they had only days before it would vanish. In Chile, the Swope telescope at Las Campanas Observatory was among the first to spot it. A faint new point of light that hadn't been there before, shining near the galaxy NGC 4993. Within hours, confirmation came from dozens of other observatories. the optical counterpart to the gravitational wave signal had been found. Humanity had, at last, witnessed a kilonova. The event was named GW 170817, GW for gravitational wave, and the numbers for the date it was detected. For the next several days, the world's most powerful telescopes turned their gaze toward that fading speck of light. Across every wavelength, optical, infrared, ultraviolet, X-ray, and radio, data poured in. What they saw confirmed everything theoretical astrophysicists had hoped for. The brightness of the explosion matched predictions for a neutron star merger. Its light shifted from blue to red as heavy elements formed and the debris cooled. The gamma ray burst perfectly aligned with the gravitational wave data. Even the timing of the signals, the 1.7-second delay between waves and light, fit models suggesting that gamma rays emerge only after the colliding neutron stars collapse into a black hole. Every piece of the puzzle clicked into place. This wasn't just an astronomical discovery, it was a revolution. GW 170817 marked the dawn of multi-messenger astronomy, where the universe could be observed through both light and gravitational waves simultaneously. For the first time, scientists were able to see an event unfold across the full spectrum of reality, from the distortion of space-time itself to the flash of light produced by nuclear alchemy. Einstein's century-old prediction of gravitational waves, proven only 2 years earlier, had now become a tool for exploring the cosmos. The kilonova of 2017 didn't just confirm theories, it changed them. The data revealed exactly how much material was ejected in the collision, allowing astronomers to estimate how much gold, platinum, and other heavy elements were created. The answer was astonishing. The explosion produced several Earth masses worth of gold and platinum, enough to seed entire planetary systems with precious metals. It was the first direct proof that this is how such elements are made. The jewelry we wear, the metals in our electronics, the uranium deep in the Earth's crust, all of it could trace its lineage back to events just like GW 170817. The afterglow of that kilonova lingered for weeks. Astronomers watched as it faded from blue to red, as X-rays emerged days later when the expanding jets interacted with surrounding gas, and as radio emissions confirmed the blast speed. Every observation brought new understanding. The event became one of the most studied phenomena in astronomical history. Over 70 observatories contributed data, spanning every continent and wavelength. It united scientists around the globe in a single, breathtaking moment of cosmic revelation. But perhaps the most moving part of GW 170817 wasn't the science itself, it was what it represented. For the first time, humanity had watched the universe forge matter from nothing, create light from gravity, and confirm theories that had once existed only in the minds of dreamers like Einstein. It was the ultimate symphony of creation and destruction, captured by instruments built through decades of collaboration and human ingenuity. It reminded us that even though we are small and fragile, we are capable of perceiving the grandest, most fleeting acts of the cosmos. In that one event, the chirp of gravitational waves, the flash of gamma rays, the bloom of fading light, we saw the universe speaking to us in 2 languages at once. GW 170817 was more than just a kilonova. It was the universe whispering, "You're ready to understand me now." Despite the breathtaking spectacle and the scientific revolution that GW 170817 ignited, one of the most profound truths about kilonovae remains their staggering rarity. The universe is vast beyond imagination, filled with billions of galaxies, each hosting hundreds of billions of stars. And yet, among all that cosmic abundance, kilonovae are events that occur only around 2 times in all of human observational history. To put that into perspective, Astronomers have watched thousands of supernovae, discovered millions of variable stars, and mapped untold numbers of galaxies. But the Kilonova stands apart as a true celestial rarity, a once-in-many-lifetimes convergence of impossible conditions. To understand why, one must first remember that Kilonovae require a very specific and improbable setup. They begin with not one, but two massive stars, each several times heavier than our Sun, born together in the same stellar nursery. These stars must live out their fiery lives side by side, each eventually exploding in a supernova without destroying their partner or drifting too far apart. What remains after those twin cataclysms are two neutron stars, incredibly dense, city-sized remnants of what were once colossal suns. For a kilonova to occur, both of those remnants must remain gravitationally bound, orbiting one another across millions or billions of years, their orbits decaying slowly as they emit gravitational waves. And finally, after eons of cosmic patience, they must collide. Each step in that process eliminates countless possibilities. Most massive stars never form in pairs at all. Most binary systems are torn apart by the explosive force of their supernova deaths. And even when two neutron stars do remain bound, the timescale for their eventual merger can be longer than the current age of the universe. For every galaxy like ours, an event like this might occur only once every 100,000 years, perhaps even less frequently. It is a cosmic lottery of unimaginable odds. Even when a kilonova does occur, its brief lifespan makes detection a monumental challenge. The explosion itself lasts only a matter of days before fading beyond the reach of even our most powerful telescopes. Unlike supernovae, which can remain visible for months, the kilonova's brilliance is fleeting, its light shifting rapidly through colors as it cools. Unless astronomers happen to be watching the right region of the sky at precisely the right time, the event passes unnoticed, its brilliance extinguished before we ever know it existed. The combination of extreme rarity and brevity makes every confirmed detection an extraordinary triumph of timing, technology, and human perseverance. And that's only half the challenge. Because kilonovae also emit gravitational waves, detecting them requires instruments sensitive enough to measure distortions in space-time smaller than the width of a proton. Until recently, such precision was unthinkable. For centuries, humanity studied the universe only through light, visible, radio, infrared, and X-ray. But kilonovae demanded more. They forced us to listen to the universe, not just watch it. Only after the advent of gravitational wave astronomy in the 21st century did it become possible to catch these events in the act. Without detectors like LIGO and Virgo, we might still be waiting for proof that such collisions even occur. The rarity of kilonovae also tells us something profound about cosmic evolution. These events are responsible for forging much of the universe's heavy elements: gold, platinum, uranium, and others. Yet they happen so infrequently that the material they produce must spread widely, carried across galaxies by stellar winds, radiation pressure, and time. It's humbling to think that something as common to us as a gold ring traces its lineage to an event that might only happen once in 100 millennia in any given galaxy. The heavy metals on Earth, the ones that fill our planet's crust and run through our technology, are the scattered remains of a handful of explosions that occurred billions of years before our solar system even formed. But rarity often amplifies beauty, and in that sense, kilonovae embody one of the universe's greatest paradoxes, that something so infrequent can have such a profound impact. They may happen only around 2 times in the span of human observation, but their echoes are everywhere, in our jewelry, our electronics, our very biology. Each atom heavier than iron, Each glimmer of gold or streak of uranium carries the fingerprint of some long-forgotten merger, the remnants of two dead stars locked in an eternal embrace. Astronomers sometimes describe the challenge of finding another kilonova as catching lightning in another galaxy. Even with the most advanced observatories on Earth and in orbit, predicting when and where one will occur remains nearly impossible. It's not just about having the right instruments, it's about cosmic luck. The gravitational wave signal has to be strong enough, the explosion bright enough, the distance close enough, and the alignment favorable enough for us to see it. Miss that brief window, and the light is gone forever, leaving only ripples in space-time as a silent record of what occurred. That's why the discovery of GW 170817 was more than just a scientific event. It was a near miracle of timing. It reminded astronomers how precious each detection truly is, how much coordination and luck are required for the universe to reveal its secrets. We may not see another confirmed Kilonova for decades. Perhaps one is happening right now, somewhere beyond our reach, its light racing toward us through the cosmic dark. Maybe in a century or 1,000 years, that light will finally arrive, and future astronomers will marvel at it the way we did in 2017. In a universe where stars explode every second and galaxies collide by the millions, the kilonova remains a whisper, a soft, fleeting pulse of creation amid the cosmic roar. Its rarity is part of its majesty. It reminds us that not every secret of the cosmos is loud or frequent. Some are hidden, waiting patiently for the right moment to be seen. And when they finally are, they change everything. When we speak of the rarity of kilonovae, it's easy to think of them as quiet whispers of the cosmos, brief, fleeting, and subtle. But that couldn't be further from the truth. Rarity, in this case, does not mean smallness. A kilonova may last only days, but in those short moments, it releases more energy than almost anything else in the known universe. To witness such an event, even from millions of light years away, is to see a burst of power so immense that it defies comprehension. This is not just another stellar explosion. It's the cosmic equivalent of 1 billion suns igniting at once. At the moment of collision, the two neutron stars, each only about 20 kilometers wide, yet heavier than the Sun, merge with such violence that they unleash an energy output that can briefly rival the total light of an entire galaxy. In mere seconds, a kilonova radiates as much energy as all the stars in the Milky Way combined emit in the same amount of time. It's a scale that stretches the limits of human imagination. Our brightest atomic bombs, our most powerful fusion experiments, even the total energy output of humanity across all of history, all of it pales into insignificance next to what unfolds in that one brief cosmic instant. To begin to grasp that magnitude, picture the Sun, a sphere of nuclear fire burning at 15 million degrees Celsius, pouring out light and heat every second for billions of years. Now imagine multiplying that by 1 billion, and then compressing that energy into the span of a heartbeat. That is what happens in a kilonova. The amount of energy radiated in gamma rays, light, neutrinos, and gravitational waves during the collision would vaporize anything within millions of kilometers. Even if a kilonova occurred at the distance of the nearest star to Earth, Alpha Centauri, its light would be so intense it could outshine our Sun for days, and its radiation would strip the atmosphere from our planet. But what truly humbles scientists isn't just the raw output. It's the variety of energy forms produced. Unlike a supernova, which primarily releases energy through light and shock waves, a kilonova floods the universe with every type of energy known: high-energy gamma rays, blinding optical light, long-lasting radio afterglows, neutrino bursts, and gravitational waves that ripple through space-time itself. It's a cosmic symphony where every instrument, matter, light, gravity, and motion, plays its part in perfect, terrifying harmony. Each form of energy reveals a different layer of the explosion's story, allowing astronomers to piece together how matter behaves under the most extreme conditions imaginable. And yet, this unimaginable power is not chaotic. There is structure in the storm. The energy doesn't simply explode outward in every direction. It forms focused jets that shoot out from the poles of the merging stars. These gamma-ray jets move at nearly the speed of light, tunneling through the debris cloud and piercing the void of space like cosmic lighthouses. Each beam carries the energy equivalent of millions of supernovae. If one of these jets happens to point toward Earth, it appears to us as a brief but incredibly bright flash, a short gamma-ray burst. For years, astronomers puzzled over the origins of these bursts. It was only after the Kilonova of 2017 that the mystery was solved. They are the fingerprints of colliding neutron stars, the visible heralds of spacetime's most powerful convulsions. Even the gravitational waves produced in a kilonova are a form of energy on a scale that staggers belief. The amount of energy radiated through spacetime distortions alone can exceed the total mass of the Earth converted entirely into pure energy. Think about that for a moment. An entire planet's worth of mass annihilated into waves that ripple invisibly across the cosmos. When these waves reach Earth, billions of years later, their effects are so faint that they stretch our planet by less than 1,000th the width of a proton. And yet, those whispers carry with them the echo of that colossal explosion, allowing us to measure an event that occurred before life even existed here. This scale of energy isn't just destructive, it's creative. The light of a kilonova doesn't merely signal an explosion. It announces the birth of new elements, new matter, and the continuation of cosmic evolution. That immense outpouring of power is what forges gold, platinum, and other heavy elements, hurling them into interstellar space to seed future stars and planets. In a sense, the kilonova's violence is what makes existence possible. Its fury is life's foundation. Without such vast energy transitions, the universe would remain chemically barren. No planets, no oceans, no life. To truly feel the magnitude of a kilonova, you have to step outside human scales entirely. On Earth, even our most powerful explosions release energy measured in megatons or gigatons of TNT. The entire nuclear arsenal of humanity combined would barely reach joules. A kilonova, by contrast, can release up to 26 orders of magnitude greater. That's a number so large it's almost meaningless. It's enough to boil every ocean on Earth trillions of times over, enough to unmake entire solar systems. And yet, all of that power originates from two objects no larger than a city. The enormity of that fact almost borders on the spiritual. Two remnants of long-dead stars, spinning silently for billions of years, collide for less than a second, and in that instant, they release enough energy to reshape galaxies, forge worlds, and write the next chapter of cosmic history. It's as if the universe has hidden within its smallest, densest forms the power to recreate itself. Every kilonova is a reminder that the cosmos holds forces far beyond our comprehension, energies that operate on scales we can only describe with awe. When astronomers recorded the light and waves from GW 170817, they were not just collecting data, they were bearing witness to an act of cosmic creation. For a few fleeting seconds, the universe revealed its raw power, its capacity to both destroy and build, its ability to compress eternity into a moment of blinding brilliance. That light has long since faded, but the energy it unleashed still moves outward, still ripples through the fabric of space, still carries within it the story of what we are made of. In every sense, the kilonova is a paradox, impossibly brief, yet unimaginably powerful, vanishingly rare, yet profoundly influential, destructive beyond measure, yet responsible for the beauty of existence. To feel the magnitude of its energy is to glimpse the heartbeat of the universe itself, a pulse so strong it can be felt across time, resonating through every atom that was ever forged in its fire. When the blinding light of a Kilonova fades, when the cosmic roar of its energy quiets into the silence of space, the question remains: what happens after? What is left behind in the wake of such unimaginable destruction? The answer is as profound as the event itself. For what remains is not just debris or radiation, but a remnant that reshapes the universe around it. Sometimes a black hole, sometimes a hypermassive neutron star, and always a scar on space-time that will last for eternity. As the two neutron stars collide, their combined mass often exceeds the limit that a single neutron star can support. The immense pressure of gravity crushes their already dense matter even further, overwhelming the forces that hold atomic nuclei apart. When that threshold is crossed, around 2.5 to 3 times the mass of our Sun, there is only one possible outcome: a black hole. In that instant, matter collapses beyond comprehension, falling inward faster than light itself can escape. A singularity is born, hidden behind an event horizon, a boundary beyond which nothing, not even information, can return. This newborn black hole is surrounded by a turbulent disk of glowing material, the remains of the two neutron stars that didn't fall in immediately. This disk swirls around the black hole at near light speeds, heated to billions of degrees, radiating X-rays and gamma rays into the void. It's a chaotic, violent environment, but also one of creation. The magnetic fields generated by this swirling plasma can launch twin jets of energy that blast outward, cutting through the surrounding debris. These jets, moving at nearly the speed of light, are what produce the short gamma ray bursts that first alert us to a Kilonova's existence. For a few seconds, the black hole feeds, devours, and shines like a beacon before settling into eternal darkness. But not every Kilonova ends with a black hole. Sometimes, the merging neutron stars form what's known as a hypermassive neutron star, a transitional object that defies the normal limits of physics. These colossal remnants are balanced precariously between existence and collapse, supported temporarily by their own rapid rotation and intense magnetic fields. Imagine a sphere no larger than a city, spinning hundreds of times per second, generating magnetic fields a quadrillion times stronger than Earth's. For a brief period, perhaps seconds, minutes, or even hours, this hypermassive neutron star radiates energy like a cosmic dynamo, its surface glowing with unimaginable heat and its magnetic poles emitting fierce beams of radiation. During this short lifetime, it can profoundly affect its surroundings. The powerful magnetic fields drive winds that push material outward, while its rapid spin amplifies the energy of the explosion, brightening the Kilonova's afterglow. But this state cannot last forever. Eventually, as the hypermassive neutron star loses energy through radiation and gravitational waves, it slows, its internal pressure falters, and gravity finally wins. It collapses inward, becoming a black hole, the inevitable conclusion of its brief, brilliant existence. In both outcomes, the result is final: the ultimate expression of cosmic gravity, a point of no return carved into the structure of the universe. Even though the immediate violence of the collision subsides, the aftermath continues to echo for eons. The material thrown into space, enriched with newly forged elements, expands outward, cooling and blending into the interstellar medium. Over millions of years, that material becomes part of new star-forming regions, merging with gas and dust clouds to form future generations of stars and planets. The atoms of gold, platinum, and uranium, born in that single explosion, will one day become part of the crusts of new worlds, buried deep within their surfaces or shining brightly in the form of jewelry crafted by intelligent beings far in the future. Astronomers can even track this evolution long after the initial light fades. The blast wave from a kilonova continues to move outward, interacting with interstellar gas and leaving a faint radio afterglow that can last for years. These afterglows allow scientists to map the explosion's energy, direction, and expansion speed, revealing how matter behaves under the most extreme conditions. The gravitational waves, too, continue their journey, spreading indefinitely through the cosmos. Faint ripples that, in principle, will never fully disappear. They carry with them the eternal record of what occurred, a silent signature inscribed into the geometry of space-time itself. But perhaps the most extraordinary legacy of a kilonova lies in its ability to permanently alter its galactic neighborhood. The heavy elements it releases enrich its host galaxy's chemical composition, setting the stage for the formation of complex matter elsewhere. The black hole it leaves behind may eventually merge with another, forming an even larger one and sending out another round of gravitational waves billions of years later. The fabric of space is stretched, distorted, and rewritten by the event, ensuring that nothing, not even the emptiness around it, remains untouched. If you could somehow travel to the site of a kilonova long after it faded, you would find a region scarred yet hauntingly beautiful. A vast bubble of enriched gas expanding outward, faintly glowing as it cools. At its heart, invisible but undeniable, a black hole or a remnant neutron star would remain, quietly bending light and time around itself. Everything that once was, two ancient stars, their shared orbit, their final collision, would be gone, replaced by something new. The universe, in its own way, has turned death into transformation, and that is the true power of a kilonova. It doesn't simply destroy, it renews. It doesn't just end two stars' lives. It gives birth to something enduring. The universe after a kilonova is not the same as the one before. Its matter, its light, its very geometry are changed. Every such event is both a funeral and a genesis, a cosmic moment of renewal written in the deepest language of physics. When we look at the stars and wonder where everything came from, the metals in our hands, the gravity that shapes galaxies, the elements that make up our bodies, the answer lies in events like these. Every kilonova leaves behind not just remnants, but meaning. It tells us that even in the aftermath of unimaginable violence, the universe continues to evolve, to build, to create. In the wake of annihilation, new beginnings are born. And through that eternal cycle, the cosmos ensures that nothing, not even destruction, is ever truly the end. Long after a kilonova's blinding light fades and its shockwaves disperse into the great silence of the cosmos, its true legacy begins, the quiet, steady enrichment of the universe. Though the event itself lasts mere days, its influence spans billions of years. Every kilonova, rare as it is, becomes a kind of cosmic gardener, sowing the seeds of complexity throughout its galaxy. It is within these cataclysmic collisions that the heavy elements, the building blocks of planets, oceans, technology, and even life, are forged and scattered into the interstellar medium. Without them, the universe would be little more than a vast expanse of hydrogen and helium, simple, luminous, but lifeless. Before kilonovae were confirmed, scientists long puzzled over where the universe's heaviest elements came from. Supernovae, powerful as they are, could explain the creation of elements up to iron. Beyond that point, however, fusion ceases to generate energy. It consumes it. Something far more extreme was required to explain the presence of gold, uranium, and other heavy metals scattered throughout galaxies. The discovery of kilonovae filled that missing gap in cosmic history. These stellar collisions are not just explosions. They are alchemical events on a galactic scale, transforming the simplest ingredients of the universe into the most complex. When two neutron stars merge, the extreme conditions, immense gravity, staggering heat, and an abundance of free neutrons, create the perfect environment for the rapid neutron capture process, or R process. In just seconds, atomic nuclei are bombarded by neutrons faster than they can decay, creating elements far heavier than iron. These newly minted atoms are then flung outward at a significant fraction of the speed of light, dispersed across interstellar space. Over eons, they mix with clouds of hydrogen and helium, enriching them with the material needed to form new generations of stars and planets. This cycle of creation, destruction, and renewal is what drives cosmic evolution. Galaxies are not static structures. They are living ecosystems, constantly reshaped by the births and deaths of their stars. Each kilonova adds to this process by injecting its surroundings with the rarest elements, the heavy metals astronomers refer to when discussing a galaxy's maturity. The more kilonovae and supernovae a galaxy has experienced, the more chemically rich it becomes. Over billions of years, this enrichment changes the types of stars that can form, the nature of the planets that orbit them, and even the possibility for life itself to arise. Take Earth, for example. Our planet is built from the remnants of ancient stellar explosions. The iron in our blood, the calcium in our bones, the silicon in our rocks, and the gold in our jewelry all trace their origins to events like kilonovae. Billions of years before the Sun was born, somewhere in a corner of the Milky Way, two neutron stars collided. Their ashes drifted through the galaxy, merging with clouds of gas and dust. When those clouds eventually condensed to form our solar system, that enriched material became part of the planets, including Earth. In a very literal sense, we are made of stardust forged in cosmic violence. Every breath we take and every metal we touch is an echo of that ancient explosion. Kilonovae also play a subtle but vital role in determining the diversity of planets across the universe. The presence of heavy elements allows for the formation of rocky worlds like Earth, Mars, and Venus. Without them, only gaseous planets like Jupiter or Saturn could exist. Metals, in the astronomical sense, act as the scaffolding of planets and moons, forming cores, crusts, and the minerals that make complex chemistry possible. Even the radioactive isotopes produced in kilonovae, such as uranium and thorium, contribute to a planet's internal heat. On Earth, their slow decay keeps our planet's core molten, driving plate tectonics, volcanic activity, and the magnetic field that shields us from cosmic radiation. In this way, the echoes of kilonovae continue to shape the very conditions that sustain life. But the impact doesn't stop at the planetary level. It extends to biology itself. The heavy elements synthesized in these collisions form the essential ingredients of living organisms. Iron, which allows our blood to carry oxygen. Iodine, crucial for hormones. Zinc, copper, and manganese, vital for enzymes and DNA. All of them are children of neutron star mergers. Even the tiny quantities of gold used in medical devices or the platinum in electronic circuits serve as reminders that the human body and its creations are part of the same cosmic story. We are literally the product of kilonovae, matter born in death, reborn as life. It's extraordinary to think that the universe's most violent moments are also its most creative. A kilonova may destroy two stars, but in doing so, it lays the groundwork for galaxies to evolve, for planets to form, and for life to emerge. It transforms simplicity into richness, chaos into structure, and death into continuity. Without such rare events, the universe would be uniform, sterile, and unchanging. A place of perpetual light, but no shadow, no contrast, and no complexity. From a cosmic perspective, kilonovae are the great equalizers of existence. They ensure that no region of space remains forever primitive. Over time, their ejecta, the radioactive dust of creation, drifts through galaxies, eventually finding its way into the birthplaces of new stars. This recycling process means that even the most distant corners of the cosmos carry the fingerprints of long-dead stars. Every twinkle we see in the night sky is, in part, a reflection of past Kilonovae, their remnants now glowing as part of something new. So when astronomers say that Kilonovae enrich galaxies, they mean it quite literally. They enrich them chemically by seeding them with elements. They enrich them physically by influencing how matter clusters and evolves. And they enrich them existentially by weaving together the story of death and rebirth that defines the universe itself. The role of Kilonovae in cosmic evolution is nothing less than foundational. They are the silent architects of complexity, rare, fleeting, and yet indispensable. Every gold ring, every planet, every heartbeat owes its existence to the ashes of these cataclysmic events. The universe, through Kilonovae, transforms destruction into creation, ensuring that even in its rarest moments, it continues to build, to evolve, to live. When scientists first detected the faint ripples of space-time from a kilonova, they weren't just confirming a spectacular cosmic event, they were witnessing the culmination of one of the greatest scientific predictions ever made. The discovery didn't just expand our understanding of the universe, it changed how we study it. The kilonova didn't only shine light on the cosmos, it gave us a new way to listen to it. This was the dawn of the gravitational wave revolution, a moment when Einstein's century-old theory finally stepped out of mathematics and into the realm of observation. To understand why this was revolutionary, we have to go back to 1916. That was when Albert Einstein, having just completed his general theory of relativity, made a bold prediction. Massive objects moving through space-time could create ripples, like stones tossed into a cosmic pond. These ripples, called gravitational waves, would travel outward at the speed of light, carrying with them information about their cataclysmic origins. But Einstein himself wasn't sure they could ever be detected. The waves would be unimaginably faint, their distortions smaller than a fraction of a proton. For decades, physicists debated whether they even existed at all. Fast forward a century. After decades of engineering, innovation, and persistence, humanity built machines sensitive enough to measure these whispers of the universe. The Laser Interferometer Gravitational Wave Observatory, or LIGO, along with its European counterpart, Virgo, became our ears in the cosmic dark. These instruments could detect changes in space-time smaller than 1/10,000th the diameter of an atomic nucleus, an accomplishment so precise that Einstein himself might have considered it impossible. The first detection came in 2015 when LIGO recorded the gravitational waves from two colliding black holes. It was a historic moment, confirming that Einstein's ripples were real. But black holes, by their nature, emit no light. They are purely gravitational creatures. The next great leap came 2 years later, in 2017, when the universe presented us with something different. A collision of two neutron stars, an event capable of producing both gravitational waves and light. That event, known as GW170817, became the most significant milestone in modern astronomy since Galileo first pointed a telescope at the stars. When the gravitational wave signal from GW170817 reached Earth, LIGO and Virgo captured it almost simultaneously, allowing scientists to triangulate its position in the sky. Just seconds later, space telescopes detected a corresponding burst of gamma rays. This marked the first time in history that a cosmic event had been observed through both gravitational and electromagnetic messengers. Sound and sight united in a single cosmic symphony. This union of gravitational and light-based observation confirmed not just Einstein's predictions about space-time, but something far greater, that the universe could be experienced in entirely new dimensions. No longer were astronomers confined to studying light. The visible, radio, X-ray, and infrared signals that stars and galaxies emit. They could now detect motion itself, the shaking of the very fabric of reality. Einstein's equations had become a bridge, connecting the abstract mathematics of relativity with the tangible, observable universe. The Kilonova of 2017 was, in essence, a cosmic experiment that no human could ever reproduce in a lab. It confirmed Einstein's vision with exquisite precision. The gravitational waves arrived at Earth first, followed 1.7 seconds later by the gamma-ray burst. That tiny delay was perfectly consistent with the idea that both light and gravity travel at the same speed through the vacuum of space, as Einstein had proposed. It also ruled out countless alternative theories of gravity that had tried to challenge relativity. In one event, lasting only moments, the universe validated the most elegant framework for understanding itself. The theory that space-time is not a static stage, but a living, dynamic fabric, capable of bending, rippling, and carrying information across billions of light years. But this wasn't just a triumph of theory. It was the beginning of a revolution in how we study the cosmos. Before gravitational wave astronomy, we could only observe the universe through what it chose to emit as light. That meant vast regions remained forever hidden: black holes, dark matter, neutron star interiors, phenomena that emit little to no electromagnetic radiation. Gravitational waves, however, are indifferent to light and darkness. They pass through matter unimpeded, carrying pristine information about their source. This allows us to observe events that would otherwise be invisible. The discovery of Kilonovae through gravitational waves and light together, what we now call multi-messenger astronomy, opened the door to a completely new understanding of astrophysics. With gravitational waves, we can hear the inspiral and merger of massive objects, like a faint cosmic heartbeat. With light, we can see the debris, the explosions, and the formation of new matter. Together, they allow us to reconstruct every stage of the event, from the first gravitational tremor to the final flash of light. Einstein's ripples have now become one of the most powerful tools in science. Each new detection tells us not just where and when something happened, but how space-time itself behaved in that moment. Gravitational wave astronomy has revealed entire populations of black holes that were previously unknown, measured the expansion of the universe with unprecedented accuracy, and even tested the limits of relativity itself. But it was the Kilonova, the beautiful violent collision of two neutron stars, that proved this new science could bridge the gap between theory and observation, between sound and sight, between math and meaning. The implications stretch far beyond the study of stars. The same methods used to detect gravitational waves from Kilonovae may one day reveal clues about the earliest moments of the Big Bang, when space-time itself first began to ripple. They might uncover the secrets of dark matter, or even detect exotic phenomena like cosmic strings or wormholes. The Kilonova was not the end of discovery. It was the beginning of an era where the universe communicates with us in ways we are only beginning to comprehend. And perhaps the most poetic part of this revolution is how quiet it is. The signals from these events are faint, subtle, and fleeting, yet they carry the weight of creation itself. Einstein once said that the most incomprehensible thing about the universe is that it is comprehensible. The discovery of gravitational waves and their connection to Kilonovae is living proof of that. From the faintest tremor of space-time, we've learned to read the story of cosmic evolution. From the tiniest distortion, we've confirmed the deepest truths about reality. So when the detectors hum with that rising chirp, and the telescopes capture a brief flash of light, we're not just observing another astrophysical event, we're witnessing the universe speaking to us in its purest language, the vibration of existence itself. The Kilonova was the voice that carried Einstein's century-old whisper across the cosmos, and humanity finally heard it. Ever since that groundbreaking moment in 2017, when the universe first revealed the light and sound of a kilonova through GW 170817, the scientific world has been waiting, watching the skies with an intensity never seen before for the next one. That event changed everything. It proved that these rare cosmic collisions are real, that they shape galaxies, and that they give birth to the heavy elements that make planets and life possible. But it also set in motion a new era of relentless pursuit, a cosmic treasure hunt unlike any other. Today, scientists across the globe are on high alert, united by a single goal: to catch another kilonova in the act. The challenge, however, is immense. These events are fleeting, unpredictable, and happen perhaps once every 100,000 years per galaxy. Yet, in a universe containing over 2 trillion galaxies, somewhere out there, right now, 2 neutron stars are spiraling toward each other, their final collision destined to light up space-time once again. The question isn't if we'll see another kilonova, it's when and whether we'll be ready. The search begins not with telescopes that look for light, but with instruments that listen for the faint tremors of space-time itself. The LIGO and Virgo observatories and their Japanese counterpart, KAGRA, are humanity's gravitational ears. They scan the universe continuously, using exquisitely precise lasers to detect the smallest distortions imaginable. When 2 neutron stars begin their final spiral, they send out gravitational waves that ripple through the cosmos, and when those waves reach Earth, they stretch and compress our planet by less than the width of a proton. Yet, those whispers are enough. The moment LIGO or Virgo detects such a signal, an alert goes out to the entire global astronomy community within seconds. Hundreds of observatories, both on Earth and in space, immediately swing their instruments toward the region of sky where the signal originated. It's a race against time, because if it is a kilonova, its light will only shine for a few days before fading forever. The first flashes are often detected in high-energy gamma rays, followed by visible and infrared light, and finally radio waves as the debris expands into space. By combining all these signals, scientists can reconstruct the event from its first gravitational tremor to its last faint photon. In the years since GW 170817, LIGO and Virgo have recorded hundreds of gravitational wave signals, most of them from merging black holes. But among these, scientists continue to hunt for that distinctive signature that marks a neutron star collision. The pattern is unmistakable: a long rising chirp lasting several seconds, growing in frequency as the stars draw closer. Each detection prompts a flurry of observation: telescopes scanning the heavens, computers running simulations, researchers comparing data from across the globe. It's the most collaborative endeavor in modern science. Thousands of minds united by the faintest echoes from the edge of the universe. And the search is only getting better. Over the past few years, LIGO and Virgo have undergone major upgrades, increasing their sensitivity and range. They can now detect mergers from farther away, hundreds of millions of light years beyond what was possible in 2017. Soon, another observatory, LIGO India, will join the network, adding more triangulation points to pinpoint events more precisely. But the most exciting development lies on the horizon. The next generation of detectors, the Einstein telescope in Europe, the Cosmic Explorer in the United States, and the Laser Interferometer Space Antenna, or LISA, which will orbit the Sun. LISA is especially ambitious. It will be the first gravitational wave detector in space. Instead of using tunnels a few kilometers long, LISA will separate its laser-equipped spacecraft by millions of kilometers, forming a vast triangle that can detect low-frequency gravitational waves that ground-based observatories can't. Scheduled for launch in the 2030s, it will open a new window into the cosmos, able to detect not only neutron star collisions, but also mergers of supermassive black holes and possibly the faint relic waves from the birth of the universe itself. Together, these observatories will make the universe transparent in ways we can scarcely imagine. But finding the next kilonova isn't just about technology. It's about coordination and timing. Every successful detection requires an intricate dance between instruments, observatories, and scientists across the world. Space-based telescopes like JWST, the James Webb Space Telescope, and Hubble are crucial for capturing the infrared afterglow, while ground-based giants like the Very Large Telescope, Gemini Observatory, and Subaru provide detailed spectroscopic data to analyze the chemical fingerprints of newly formed elements. Even smaller robotic telescopes contribute, scanning wide areas of sky in search of that telltale flicker of light. Each alert sets off a global cascade of action, an international relay race against time. Within minutes of a gravitational wave signal, teams across continents coordinate, sharing data in real time, scheduling observations, and analyzing spectra as the light evolves hour by hour. The collaboration is so vast that it involves thousands of scientists from over 100 institutions. And when a candidate is found, a new point of light that wasn't there the night before, the excitement is electric, because it could be the next one. It could be the second confirmed Kilonova, the next step in unraveling how the universe creates matter itself. The quest to find another Kilonova is more than a scientific pursuit. It's an existential one. Every detection deepens our understanding of the universe's story and our place within it. These events remind us that creation and destruction are intertwined, that even in the darkest reaches of space, rare and beautiful things happen that shape everything we know. For many astronomers, finding another kilonova would be like capturing lightning in a bottle, a chance to witness, once again, the universe forging the elements of existence from the remnants of death. And as humanity's tools grow more powerful, so too does our ability to listen to the cosmos. Somewhere, perhaps even now, two neutron stars are circling ever closer, their orbit decaying with every passing moment, their gravitational whispers already traveling toward us. They will collide one day, perhaps tomorrow, perhaps 1,000,000 years from now, and when they do, their light will reach our telescopes, their waves will shake our detectors, and their story will join the growing chorus of cosmic creation. Until then, the world waits, not in silence, but in anticipation. Every hum of LIGO, every alert from Virgo, every glimmer in the night sky could be the one. The next kilonova, another message from the deep, another spark of creation written across the vast and eternal dark. Even with all our instruments tuned to the cosmos, all our satellites sweeping the skies, and all our detectors listening to the faint tremors of space-time, the odds of seeing another kilonova are almost laughably small. It's like standing on Earth during a thunderstorm and trying to catch lightning striking twice, not just nearby, but in another galaxy, millions of light years away. That's what astronomers are up against. Every known factor conspires against such a discovery. The rarity of the event, its brief duration, its unpredictable timing, and the vastness of space itself. And yet, this very improbability is what makes the hunt so electrifying. To glimpse a kilonova, the universe has to align in a near-perfect act of cosmic choreography. Two neutron stars must first exist in the same binary system, orbiting each other for billions of years. Then, their orbits must decay just enough for them to collide, something that happens maybe once every 100,000 years in a galaxy like ours. Their light and gravitational waves must then travel unimpeded through space, crossing the endless dark without being obscured by dust or cosmic interference. Finally, when that light and those waves reach Earth, we must happen to be looking at just the right patch of sky, at just the right time, with the right instruments and the right attention. One missed signal, one cloudy night, one delay of even a few hours, and it's gone, vanished forever into history. Imagine the scale of that challenge. The observable universe contains over 2 trillion galaxies. Every second, somewhere out there, stars are dying, black holes are merging, and galaxies are colliding. But among all those countless events, a kilonova happens only occasionally, and its light fades within days. Even for a universe that's been running for 13.8 billion years, that's a blink in cosmic time. To catch one in progress is almost like catching the exact moment a soap bubble bursts from across an ocean through a keyhole with your eyes closed. That's why the discovery of GW170817 felt like a miracle. For decades, the concept of a neutron star merger was something that lived only in equations and simulations. Scientists knew they must exist. After all, the laws of physics demanded it. But to see one, to record both its gravitational heartbeat and its flash of light, seemed impossibly lucky. When it happened, it was as though the universe itself had briefly decided to lift its veil and let us peek behind the curtain. Since then, humanity has waited, detectors ready, telescopes scanning, software constantly sifting through billions of signals for that one telltale pattern. The long, rising chirp that means 2 neutron stars are spiraling together in their final dance. The data streams never stop. Every night, thousands of computers across the world listen for the faintest ripple in space-time, filtering out noise from earthquakes, human activity, and random vibrations. Each time a potential signal appears, astronomers hold their breath. Is this it? Could this be another? But so far, the universe remains silent, patient, secretive. That silence, though, is not discouraging. It's humbling. It reminds scientists that nature doesn't perform on command. The cosmos reveals its wonders on its own schedule, indifferent to our impatience. When the next kilonova comes, it will not announce itself. It will erupt in some distant corner of the universe, flash brighter than a galaxy, and then fade back into nothingness. And if we are lucky, if our detectors are awake, if our telescopes are pointed true, if our algorithms are fast enough, we might just catch it. What's extraordinary is that despite the odds, we now can. A century ago, such an idea would have been pure fantasy. Even the most advanced observatories of that time could never have dreamed of detecting something so faint, so distant, and so brief. But now, with instruments like LIGO, Virgo, and the soon-to-be-launched LISA, we've reached the point where we can listen to the heartbeat of the universe itself. We can detect vibrations from objects billions of light years away, signals that have been traveling since before Earth even formed. The odds are still astronomically low, but for the first time in history, they're not impossible. And perhaps that's what makes each detection so meaningful. When astronomers speak about the next kilonova, there's a sense of reverence, even emotion, because they know that everyone we catch is a cosmic gift, a message sent across time and space, bearing news from the most extreme frontiers of physics. Every detection isn't just a data point, it's a story, a piece of the universe's autobiography. Even so, the rarity of kilonovae gives them a kind of mythic quality. They are the phoenixes of the cosmos, rising out of the ashes of dead stars, to scatter gold and platinum across galaxies. To witness one is to see the cycle of creation itself unfold, death becoming birth, destruction becoming genesis. And because we've only ever seen around 2 in all of history, each one feels sacred, as though the universe is sharing a deeply personal secret. When the next one comes, and it will, the world will stop again. Scientists will drop everything to track it, telescopes will pivot across the skies, and gravitational wave detectors will hum with data. For a few days, humanity will once again stand together under the same sky, united by a single point of light that connects us to the deepest processes of existence. And then, as suddenly as it appeared, that light will vanish, leaving behind only data, memory, and awe. Because that's the essence of the Kilonova. It doesn't just remind us how vast and powerful the universe is, it reminds us how fleeting its wonders can be. Even with all our science, all our technology, and all our vigilance, catching one in action is still like catching lightning striking twice, not just in another country, not even on another continent, but in another galaxy entirely. And yet, we'll keep watching, listening, and waiting. Because in the silence of space, we know that somewhere out there, the next flash is already on its way. When you think about gold, the warm glimmer in a wedding ring, the intricate wiring inside your phone, the ancient coins buried beneath the earth, it's easy to see it as something earthly, something human. But in truth, gold is not of this world. It was not born in volcanoes, nor forged in the heart of any ordinary star. Its story stretches back billions of years, long before Earth existed, long before the sun even lit the sky. Every speck of gold that has ever gleamed, every atom that glitters on a finger or powers a circuit, was forged in the unimaginable violence of a Kilonova. The jewelry we wear and the technology we use are, quite literally, the ashes of colliding stars. After all the cosmic drama, the dance of neutron stars, their final collision, the explosion of light and energy brighter than a galaxy, what remains are the elements of creation itself. In that chaos, in those fractions of a second, when temperatures soar into the billions and matter is compressed beyond comprehension, atomic nuclei fuse into new forms. Among those newborn atoms is gold, rare, stable, and radiant. In the turbulent wind of the Kilonova's debris, gold atoms scatter through the surrounding space, mixing with platinum, silver, and other heavy elements. These particles drift through the galaxy for eons, carried by stellar winds, supernova shockwaves, and gravitational tides. Eventually, those atoms find their way into giant clouds of gas and dust, the nurseries of new stars. Within these clouds, gravity begins to pull matter together, forming new suns, new planets, and new moons. Our solar system was one such place. Around 4.6 billion years ago, it coalesced from a swirling disk of material that had been enriched by generations of stellar deaths and, crucially, by at least one ancient kilonova. That means the gold, platinum, and uranium that now lie within Earth's crust, and even within our bodies, were created in some distant explosion, perhaps billions of light years away, long before life ever arose to appreciate them. Every gram of gold mined from the earth, every wedding band that symbolizes love, every ancient crown or relic ever crafted, all trace their origins to the collision of 2 neutron stars. It's an idea that humbles the imagination. The ring on your finger may contain atoms born in a firestorm that once outshone an entire galaxy. The gold that rests quietly on your skin today was once part of an explosion so fierce that it bent space-time and rippled through the fabric of the cosmos. Scientists estimate that a single kilonova can produce several Earth masses worth of gold and platinum. That's enough to fill entire oceans with precious metal. And yet, because these events are so rare, the total amount scattered across the galaxy remains minute. That's why gold is precious, not because of its luster, but because of its cosmic scarcity. It is the product of nature's most extraordinary alchemy, the kind that happens only around 2 times in all of human observation. But it's not just gold. The same collisions that create it also forge uranium and thorium, the radioactive elements that keep Earth's core hot and its magnetic field alive. Without those elements, our planet might be a cold, barren rock, its atmosphere stripped away, its surface frozen. In that sense, Kilonova didn't just give us beauty and wealth, they gave us life itself. They ensured our world would be dynamic, geologically alive, and capable of sustaining the complexity we now take for granted. There's a quiet poetry in that realization. Every piece of gold you see, whether in a museum, in a circuit board, or adorning someone's hand, is a message from the stars. It's proof that the universe creates beauty through destruction, that the most precious things often emerge from chaos. 2 stars died, and in their death, they gave us not only the elements that make up our world, but the materials we use to celebrate love, art, and civilization itself. The next time you look at gold, consider what it truly is. Not just a metal, not just a treasure, but a time capsule. Those atoms were forged in a cosmic fire billions of years ago, scattered across the void, and eventually gathered here, on a small blue planet orbiting an ordinary star. They have traveled through eternity to end up in your hands. The gold of today is the memory of a Kilonova that once tore the heavens apart. So when light catches on a gold ring, when a coin glimmers in the sun, or when circuits hum quietly in the device you hold, remember, you're touching the remnants of a universe that has been dying and rebirthing itself for eons. The rarest events in existence created the materials that define our lives. Each gleam of gold is a reminder that we are children of the stars, forged from their death, and living proof that the universe's greatest tragedies can give rise to its most enduring beauty. In the vast, unbroken silence of the cosmos, there comes, every so rarely, a moment when eternity itself seems to tremble. 2 dead stars, remnants of suns long gone, spiral inward through the darkness, their motion imperceptible to most of the universe. For billions of years, they circle one another, bound by gravity, whispering in gravitational waves that ripple quietly through space-time. Then, in a single instant, their long dance ends. And in that final collision, the universe holds its breath. There is no sound, no witness, no warning. And yet, from that instant of unimaginable violence, everything changes. Space bends, time wavers. Light bursts forth, brighter than a billion suns. A Kilonova is born, a moment so rare that humanity has only seen it happen around 2 times, and yet so powerful that its legacy is written across every corner of existence. Out of chaos comes beauty, out of death, creation. From the destruction of 2 ancient stars, new elements are forged. The gold in our hands, the uranium in our planet's core, the heavy metals that make life itself possible. When we look up at the stars, we often think of them as eternal, silent beacons of light that have always been and always will be. But the truth is more profound. The stars are not just lights in the sky, they are forgers, creators, storytellers. Their lives, their deaths, and their rebirths write the history of everything we are. The iron in your blood, the calcium in your bones, the copper in your brain, all of it was once stardust. The rarest, most fleeting explosions in the universe gave you form, and the remnants of those cosmic events still course through you every moment of your life. There is something profoundly humbling in realizing that the universe's most precious materials come not from peace, but from destruction. Every shimmering atom of gold was born in a violent collision that could obliterate worlds. Every element heavier than iron was created by stars that first had to die. The cosmos seems to tell us again and again that creation demands sacrifice, that even in the vacuum of space, the cycle of death and rebirth is what keeps everything alive. When astronomers detected the Kilonova of 2017, GW 170817, it wasn't just a scientific discovery, it was a revelation. For the first time, humanity truly heard the universe's voice and saw its light in unison. We witnessed space-time ripple. We watched gold being forged. We confirmed Einstein's dreams. But more than that, we were reminded of our connection to it all. The same event that shook galaxies also shaped us, our planet, our tools, our art, our very sense of beauty. We are the afterglow of that collision, the living memory of cosmic transformation. And as we stand here on our small blue world, looking into the night sky, we are staring into that same process unfolding endlessly across countless galaxies and epochs. Somewhere, perhaps right now, two neutron stars are nearing the end of their dance. They move faster with every heartbeat of the universe, their orbits tightening, their fates sealed. One day, their collision will light up the cosmos again, sending waves of gravity through space-time and a flash of light across the dark. Maybe millions of years from now, the light of that explosion will reach another civilization. Maybe they, too, will look up and realize what we have, that even the rarest events can define the meaning of existence. In the end, the story of the Kilonova is not just the story of stars. It's the story of everything. It is the story of creation through destruction, of chaos giving birth to order, of darkness giving rise to light. It's the universe reminding us that even the briefest, rarest moments can leave behind something eternal. A kilonova may last only days, but its effects span billions of years. Its brilliance fades, but its products endure. Worlds, moons, metals, life. So when you hold a piece of gold, when you marvel at the shimmer of the stars, remember what you are seeing. You are witnessing the universe's handwriting, the signature of two dead suns that gave everything they had so that new worlds could form. You are looking at the result of an explosion so rare that it may happen only once in 100,000 years per galaxy, and yet so consequential that it made every planet, every heartbeat, every glimmer of consciousness possible. In the silence of space, two dead stars collide, and from their death, new worlds are born. The rarest events can create the most precious things, and perhaps that is the greatest truth the cosmos has to offer, that even in its rarest moments, in its briefest flashes of light, the universe never stops creating. Out of endings come beginnings, and from destruction comes beauty, a beauty that lives in us, shines in the stars, and endures forever. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.